In this talk, I want to explain a systematic way to colour the vertices of a graph, it can be quite a complicated graph, in order to get an estimate on the chromatic number of the graph. That is the least number of colours one needs to colour the vertices so that no two adjacent vertices have the same colour. So this is the so-called greedy algorithm for colouring, but it requires us first of all to make a list in order of the vertices if we don't already have a list, because the result of the algorithm will depend upon the order we've chosen. So it's sometimes called the sequential algorithm because we have to take the vertices in sequence. And it's fun and quick to use, but the result will depend upon the order. So here's how it works. We have a list of colours. So initially these were integers 0, 1, 2, 3, but in practice I like using Greek letters, so I shall use alpha, beta, delta, and so on. And those are ordered in the sense that I regard alpha as less than beta, as less than gamma, and so on. So what we do is we take the vertices in order, in the order they've been given, starting with V1, and at each step we use the lowest colour possible, so that we have to always satisfy the constraint that no two adjacent vertices have the same colour. So we would start by giving V1 the colour alpha, and then if V2 is adjacent to V1, that would be given the colour beta. If not, it could be given alpha, and so on. I'll do some examples in a moment. That is the greedy algorithm. Now, once we've applied that to all the vertices, we've got to Vn, that will require a certain number of colours. And by definition, it can't require less than the chromatic number because it's satisfying the constraint at each stage. So the chromatic number is the least number of colours one needs. So if we apply this algorithm and it needs k colours, k is at least as big as the chromatic number. But the way it's working shows, if you look at how we proved the lemma in the last lecture, the number of colours the algorithm needs will never exceed capital delta plus 1, where capital delta is the maximal vertex degree, the largest of the vertex degrees. So in other words, when we apply this algorithm, it's going to require k colours, and k ranges between the chromatic number, which typically we won't know, and delta plus 1, which we will know. So I'm going to apply it to the example of the cube graph. So here we see the sort of looking at a cube, a transparent cube in perspective. Here we see the vertices and edges of a cube, or cuboid. The dimensions were relevant. So first of all, let's look at this graph, as one should always do before one starts colouring. It's easy to see that this is a bipartite graph. We only need two colours. If you start with the determination that you only need two colours, it's quite quick. You quickly find you can colour it with just two colours, as can be seen in the first picture on the left. It's equally obvious, well, it's even more obvious that all the vertex degrees are 3. It's a regular graph, a regular trivalent graph, as one says. So delta plus 1 is equal to 4. Unfortunately, that gives a sort of window of ambiguity in the sense that when we apply the greedy algorithm, we can't be certain whether it's going to give us whether it's going to use 2 colours or 3 or 4. Okay, in fact, you can get all possibilities. So let me apply the greedy algorithm, first of all, in the order in which the vertices are given on the left. So on the left, we've numbered the vertices, and I'm going to start with the least number, which is 1. So what happens is that I simply colour, of course, the result will be the same as the colours you see. Hopefully you do see them on the left. But I use Greek letters. So I'm going to start with vertex 1, and I always start with alpha. That for me is the lowest colour. So vertex 1 gets given alpha. My pen is red, so don't look at the colour of my pen. Then we go to vertex 2, and because this is adjacent to alpha, as I said before, we don't have any choice. We have to label that beta with the colour beta, the next colour in our list. Then we go to vertex 3. This is not adjacent to vertex 1, so we can use alpha again. In fact, we have to use alpha. That's what the greedy algorithm says, and students often make a mistake here. You must always use the lowest colour. That's part of the algorithm. The algorithm has to be a systematic rule that a computer can apply. So we don't have a choice here. We have to use alpha. And then vertex 4, similarly, we have to use beta. We can't use alpha because the vertex is adjacent to 2 alphas. And then we go to 5, where we can use alpha. You see it's working out as the colours did, with alpha red and beta green. 6 can be beta. 7 has to be alpha, 6 has to be beta, 7 has to be alpha, and 8 has to be beta. So that's an application of the greedy algorithm with this choice of ordering the vertices. It was a fairly natural choice because I just went around the inside square 1, 2, 3, 4, and then went to the outside square, although I don't know where I started. In the outside square I started with this 5 here. Now, it turns out that you can also, if you're unlucky and take the wrong ordering, the greedy algorithm will require a full 4 colours, its maximum. So let me just show you that happening on the right. So if I take the order on the right, in which the vertices are numbered differently, we start as before with an alpha on vertex 1, assuming we're going to start with vertex 1. The least vertex, we could have gone downwards, but I'm taking it in increasing numerical order. Then we go to vertex 2, that's not connected, so that has to be alpha again. Then we go to vertex 3, this has to be beta because it's connected to an alpha. Then we go to vertex 4, which again has to be beta. Then we go to vertex 5, but you see the problem with 5, it's connected to an alpha here and a beta there. So it can be neither alpha or beta. It has to be the next colour in the list, which is gamma. And then we go to 6. This, in case you can't quite see, this is this one here that's 6. And the same reasoning tells that this has to be gamma. This vertex 6 has to be coloured gamma. Then we go to vertex 7. Now we're in real trouble because vertex 7 is adjacent to alpha, beta and gamma. So we need a 4th colour, delta. And similarly for vertex 8, we need the 4th colour, delta. So we've actually required 4 colours applying the sequential algorithm, the greedy algorithm, for this particular ordering. So in some sense, if we just took the ordering at random, it didn't really help us find the chromatic number of this particular graph. Of course, the chromatic number, as I've typed up top, is 2. It's a bipartite graph. You can split the vertices into 2 subsets, the red ones and the green ones on the left, so that there are no edges from green to green or red to red. Now there's a sort of game underlying this procedure, because you could just sort of try and find an ordering which gives you the least number of colours, or if you're perverse, the greatest number of colours. In fact, you could even have 2 players here, and you take turns to choose vertices. So essentially, you're choosing your list of your sequence of vertices. One vertex, one player does one vertex, the other player does the next vertex, and maybe the first player is trying to minimise the number of colours, and the second player is trying to get something more like the right-hand side colouring scheme, in which we need the greatest number of colours. And maybe battling against each other, they come up with a scheme which needs 3 colours. So there is actually a link with this aspect of game theory. Let me give you now a more complicated example, namely that of the Petersen graph, which we've seen before. So again, there's a sort of, it's a solitaire game, if you like, in the sense that I haven't labelled the vertices here. So the game is to sort of see what happens if you take different different orderings of the vertices. See how many colours the greedy algorithm requires. Okay, so again, before you start doing any work, you should always sort of look at the graph and ask yourself, you know, what are the vertex degrees? Do I see any cycles? Do I see any odd cycles? Because if you see an odd cycle, well, of course, there's certainly a 5 cycle. There are lots of 5 cycles, and particularly the outside pentagon. That means that the chromatic number has to be at least 3, because, you know, even just the pentagon will require 3 colours to colour. So the chromatic number has to be at least 3. On the other hand, the vertex degrees are all 3, so we know the chromatic number can't be bigger than 4. It's a connected graph. So the greedy algorithm is going to give us 3 or 4. Well, let's just do it. Let me take an obvious ordering of the vertices. Let me just go around the outside with the pentagon 1, 2, as I did once before, 1, 2, 3, 4, 5. And then I go straight to the inner pentagram, continue going anti-clockwise, 6, 7, 8, 9, 10. Now let me just colour the vertices, again in red, with Greek letters. And as I explained, it's very quick to do this colouring. And let's see how many colours we need. So we start with vertex 1, which is alpha. And then vertex 2 has to be beta, vertex 3 has to be alpha because it's not connected to our first alpha, vertex 4 has to be beta, the lowest colour that we can colour it so as not to get the same colour on adjacent edges. And then 5, of course, because we're just going around the pentagon and it's an odd cycle, has to be the third colour gamma. And then we go to 6. Well, 6 is not connected to any alphas, so 6 has to be alpha. 7 has to be beta, not connected to any betas, can't be alpha. 8, I have to be careful now because we're getting cluttered. So 8 is connected to alpha and beta, so 8 has to be the third colour gamma. 9 is connected to alpha beta as well, in fact 2 alphas, so it too can be gamma, it's not connected to 8. And then finally 10 is connected to beta and gamma, so it can be alpha. We don't need a fourth colour. Okay, so what have we shown here? We've shown that the Petersen graph can be coloured with 3 colours. Well, it certainly can't be coloured with less because even the pentagon requires 3 colours. So we've concluded that I haven't said it below, but we've shown here that this application of the algorithm has been successful in the sense that it tells us that the chromatic number of the Petersen graph is equal to 3. Okay, but again, there's a sort of gamey thing here because you can ask, can you find an ordering for which the greedy algorithm requires 4 colours? And I honestly don't know the answer to that. My guess is no. I'll leave that as an open question to you. Can you find it? Try different orderings of the vertices, apply the greedy algorithm, which as you see is very quick to do, and see whether whether 3 colours, well, whether you ever need a 4th colour. That's obviously you can take now even more complicated graphs. All you have to do is order the vertices and you find out how many colours you need, and that may help you determine the chromatic number. But be careful, it doesn't determine the chromatic number. Absolutely. Okay, now I want to go on and just finish by listing some results, and I'll be saying more about these in the next lecture, which is actually one of those I recorded in 2020. So remember the question which I sort of asked in the previous talk was, when is it true that the chromatic number of a graph is actually less than or equal to delta? We know that it is always less than or equal to delta plus 1, but when can we assert this sharper inequality? And the answer to that question is given by this very neat theorem, so-called Brooks's theorem, which requires the graph to be connected for reasons I'll explain, obvious reasons I'll explain. And it says that it is always true that the chromatic number is less than or equal to the maximal vertex degree, delta, provided we're not dealing with a complete graph, Kn, or an odd cycle. But we know that both a complete graph, we know that a complete graph requires n colours, but delta is n minus 1. So in that case, this inequality would fail. Also, for an odd cycle, we need 3 colours, whereas for an odd cycle, or for any cycle, the vertex degrees are all equal to 2. So the maximal vertex degree is 2. But for an odd cycle, we need 3 colours, as I explained before. So in that case, the inequality will fail if it's an odd cycle. So that's Brooks's theorem. It's not too hard to prove that, but we're not going to prove it in this course. It's rather complicated. We're going to actually prove a weaker version of Brooks's theorem, much less useful, I have to say. So you should certainly know Brooks's theorem, because it will tell you that provided the graph you're given is not the complete graph or an odd cycle, you can be certain that its chromatic number is less than or equal to delta. Okay, so for example, that would tell you for the Petersen graph, without using the algorithm that we did, that the Petersen graph has chromatic number equal to 3, because the Petersen graph has delta equal to 3. So Brooks's theorem would imply that result, which we found by actually doing the colouring. I'm going to just finish with, well, there's a sort of, so Brooks's theorem is very useful, but we're not going to prove it in this generality. We're going to prove a corollary of it, namely this proposition here. And it's just, the proposition just has weaker hypotheses. So the proposition, rather than saying that the graph is not Kn or an odd cycle, it makes a much stronger hypothesis that the graph is not regular. Unfortunately, that's not great, because a lot of the graphs we want to colour are regular, so we can't apply this proposition. But equally, we know Brooks's theorem, that provided the graph is, of course, Kn and the odd cycle, they are regular graphs. So Brooks's theorem, as I say in the next talk, this certainly implies the proposition quite trivially, because Kn and the odd cycle are regular. So if it's not regular, it can't be Kn and it can't be the odd cycle. But if the graph is not regular, again, it has to be connected, then the chromatic number is less than or equal to delta. Okay, and as I say, we're going to prove this in the next lecture, older lecture, by actually constructing. It's very, very delicate, the ordering you take, you see. When I've explained for the cube graph, it made a big difference, the ordering you take. So we're going to actually construct an ordering of the vertices and then apply the greedy algorithm in the general situation. And that will establish the proof of the proposition. Okay, let me just remark that the connectedness here, both results require connected. That's a crucial hypothesis, and the reason is fairly obvious if you think about it. Namely, you don't require that the graph be connected. You could just take a graph which is the disjoint union of one of these nasty graphs. I referred to these two exceptions as nasty in the sense of colouring, because they require more colours than delta. So those are the sort of nasty graphs to colour. So we could take one of these nasty graphs, for example, K4. So here's the, I won't do the planar diagram. Here's a way of representing K4. 4 vertices. The cross at the point in the middle is not a vertex. That's K4. And I can just take that, and quite separately as a different component, I can take a 3-cycle. Here's a 3-cycle. And this is the whole graph. Graphs don't have to be connected, remember. So we take those two things, that's the graph. So we're talking about graph with 7 vertices here, so n is equal to 7. So it's certainly not a regular graph because we have different vertex degrees. And it's neither it's not K7, and it's not an odd cycle, but we need because of the bit just on the left, because of the K4, we certainly need 4 colors. Okay, so the Brooks's theorem and the proposition therefore as well fail because we need 4 colors, but the vertex degree, the maximal vertex degree for this combined graph is equal to 3. So that's why just be careful to check these hypotheses whether or not you need connected. Here it's essential that we state that the graph be connected.